Okay, let's get started. So, hello everyone. Looks like the microphone's not working here. I'm trying to use my own computer, but I do not have a converter. So, but next week I will bring my own converter.
You
So-
should see the Asian method.
Yeah,
Yeah,
but it's okay. I already set it here. So next week. Thank you.
no problem.
Okay, so this is 3650 computer system class. My name is Zemin Zhao. I'm an associate professor in the college. So a little bit. Some logistics. I usually record all my lectures and put everything on YouTube. But there are several other sections of the same class, and the other professor they're allowed to do that. So I'm not sure if I'm going to put it on YouTube, but I will still put it on cameras for sure. And even if I'm going to record this, you still need to attend the class in person because nothing can replace in-person interaction. So I hope everyone will bring a laptop to this class. We are going to have a lot of live demos. We're going to read code in this class, and there will be in-class exercise labs as well. I try to save 30 minutes every week so you guys can work on the labs and exercise, but sometimes we cover too much, so I cannot promise that. So this is our web page for the class, and this is merged for 3 different sections. So we're going to share labs, assignments, everything for those 3 sections, even the TAs we share. And during the class, feel free to interrupt me and ask questions, or if you want to drink, eat, I don't really mind. A little bit about myself. So my name is Zemi. I'm an associate professor here. I direct my own lab. I call it Cyber Space Security and the Forensics Lab. So from the name, you can guess we do all kinds of cyber security research. We call it a Cacti Lab because I stayed so many years in Arizona. So we do all kinds of system and the security research at different layers. And the best way to reach me is you can shoot me email, and you can find what I work on, what my lab work on those 2 websites. And my office hour will be Tuesday right after the class. And my office is at 177, which is 15 minutes walk from here. So you are welcome to go there, but you need to let me know if you go there because you won't really have access to the building. Also, we can meet online. Usually I do Zoom. This is a link for that. And besides my office hour, I'm also willing to meet you guys whenever you need. Just ping me, then we can set up a time. We do have 2 TAs for this class. Tashin is a PhD student. He's close to graduation actually. Then we have Swandip, who is a master student. Since we are merging 3 sections together, there are several other TAs. Maybe you can also ask questions. We don't have an office hour for them decided yet, so we will provide those kind of information next week. So I do have a YouTube channel, like I said. So all my previous classes I put on YouTube. But looks like today the microphone is not working. Even though I'm recording right now, I'm not sure if it's taking in my voice there. So on my YouTube channel, I have other classes, for example, software vulnerability and the security course I offer here, which is 5,000 level, 5770. So in that class, we do binary hacking, we hack all kinds of binary software, we find the vulnerabilities and try to exploit them. So this class is actually a requirement for that class. So after taking this class, you can take software vulnerability and security class, which I plan to offer again the next semester. We actually also have a hacking platform for that. Today we are going to use that a little bit because this is a Windows machine and I plan to do all the demos on my laptop, which is a Linux machine. So that's why I have to log in my platform, which was designed for another class. So a little bit about my research lab. So we do research in system and security. We work on all kinds of architectures. So in this class, we are going to use x86. We are going to read some x86 operating system 32-bit code. And a lot of assignment homework will be the 64-bit of x86. My research, we do a lot on ARM architectures. Some of them you are using a new Apple laptop that may be a M1 or M2 CPU. So that is a Cortex-A CPU. So most of the servers we are using right now are still x86. Some of your laptops are still x86. Then your phones, laptop, tablet, they are usually ARM-based architecture. We also work a little bit on RISC-V, FPGA, GPU, some other accelerators, especially AI accelerators. We do not only do security, we also do system, which means we want to make the systems run faster, more performant. Some problems are not necessarily security. We do security system for AI and use AI, machine learning, large language models. We also work on formal verification a little bit. And another one of my passion is to work on hacking. And every year I form a team to participate in one particular capture the flag competition. It's called the Embedded System CTF, eCTF. We have been doing that for many years, maybe 7, 8 years. And our team has been doing very well. So Northeastern had a team won the competition several years ago. And we also has been placing top 3 multiple times. So in that competition, we design a secure system and hack each other's system. So in my lab, we need all kinds of students at different levels, do all kinds of research, funded research, volunteer work, independent study, undergraduate research. It's probably a little bit early for you guys, but after taking this class, I think you will be ready. So let me know if you want to do something with me. So I also want to recruit for the next year's embedded system CTF. So this is a semester-long capture the flag competition. So some of you probably have some experience with CTF before, right? I guess. Yeah. So usually you do an online CTF, takes 24 hours, 48 hours. So this year, actually, we hosted a country-to-country CTF at Northeastern. We had a online qualify earlier this year with 500 students all over the world. So we invited 100 of them to come to Northeastern campus during the summer. And they had an in-person CTF during the summer. So that one is like a 48 hours CTF for the qualifying and the 12-hour CTF in person for the final, right? But this embedded system CTF is a little bit different because you are supposed to develop an embedded system, a secure embedded system. Not from scratch. The provider, the organizer of this competition will give you some skeleton which runs, but it's not secure and it doesn't have all the security features or functionalities. So what we need to do is to develop a secure system. So after that, we hand this platform or whatever we developed to the organizer. The organizer will embed some secrets there, then hand this platform to all other teams. So all other teams will try to exploit the vulnerabilities, all kinds of vulnerabilities of the system. So if you are interested in this, you can let me know maybe after midterm. I'm not recruiting students right now, but because this is for early January next year. So that's basically all about me. I guess we can take 2 minutes to talk about you. So some of you may already know each other, but whatever, you can chat with your neighbors because in this semester we will have several assignments and some of them will be group based. So you can pick a partner, and you are supposed to choose a partner for that assignment. So I will give you guys 2-3 minutes to talk to each other. Just talk to your neighbor.
I like it that way. So it's good for so that's the good side. It's like it's okay. I'll keep that in mind. All right. That's all I It's probably pretty good. Oh, okay.
Okay, so title of this class is computer system. This word computer system. These are all of things, and actually in this class we are covering a lot of things. So let's say if algorithms and the applications, they are the what of computing, then computer systems are the how. The deal with the mechanisms, then the algorithms and software run on physical computers. So there are a lot of layers of abstraction we need to do before we can actually run high-level applications on low-level physical machines. And so a computer system is not really just hardware or just the software, but a combination of all of them. Hardware, on top of that, usually we have an operating system, we usually have hypervisors. On top of that, we have programming languages, use different programming languages. We can develop different applications, and eventually we can make a computer usable for people or other computers, right? So computer systems are the foundation that ties together hardware and software. So that's why we need to learn computer systems. So in our college, we do not really have a computer architecture class. I think EE offers one, but CS doesn't offer one. And we do not have a systems programming class. And we do not have a class entitled operating system either. That's why this class, computer systems, somehow covers the contents of all those classes. Then obviously then we cannot go very deep. That's why we have another course with the same title, which is 5600. That is also called computer systems, and that is a cross-discipline class for undergraduates and graduates. So that class is more about operating system internals. And this class, I'm trying to cover as much internal as possible. But you guys also need other background, which we have to cover, right? So my goal is to get everyone through this because there are so many things at different layers we have to cover. And also after this class, if you want to learn more about OS internals, you will be ready to take 5600, which I do not offer, but several other professors, they offer in the college. And I do offer software vulnerability and security, which is a binary hacking class. So that is not a computer science class, but a cybersecurity class. I do have a lot of CS, also cybersecurity students and EE students in that class. So how many of you are familiar with what kind of software vulnerabilities are there? Buffer overflow, anyone heard of that? Yeah, buffer overflow, format string vulnerabilities, heap exploitation, kernel exploitation. We do all those in that class. Later, actually, we'll be able to say my platform for that class. So roughly speaking, we will cover those topics in this class. We will teach you by doing labs, how to use a computer like a developer, okay? Not just like a regular user, more like a developer. So you will play with terminals. We will cover C programming language. So obviously C programming language itself can be its own class. So we do not have a full semester to do that. We have 1 week to do that. But I will cover to the extent that you will be able to finish your homework and also be able to read the source code of the operating system we are going to study, which is x86, which is a small manageable operating system written in C. And we will learn a little bit x86 assembly because you have to write a little bit assembly and also read assembly to understand how to control the CPU. Cover a little bit of compiler, not too much. Then the main part of this class will still be operating systems, but not necessarily the internals. We will cover the concepts. We will read some code, but not the whole x86 system. So we're going to cover virtualization, which is one of the most important concepts in operating system. And actually, it's not only an important concept in operating system, it's an important concept for any computer systems. So what we are trying to do in computers is we add different layers of abstraction to hide what is going on under the hood and provide services to upper layers. So processes is one way to virtualize CPUs, and we will also talk about how to virtualize memories. Then it is related to the CPU, the inner working of CPU. There are memory management unit, MMU. There are translation nucleoside buffer, TLB, those kind of things. Those are hardware and different levels of memory, including cache, persistent storage, those. Concurrency is also what we are going to cover, which is another very important topic for OS and modern computers. So imagine data centers. So whenever you Google something or you talk to ChatGPT, you send one HTTP request to the data center. That data center, one of the dispatchers will dispatch your request into hundreds of requests to other computers. So they may be running distributedly at many different computers, CPUs or cores, and some of them may run at the same time on one core or multiple cores, one CPU. When we talk about the systems, many file systems, actually you will develop a simple file system as the second project in the semester. There will be several assignments, several labs, and 2 projects. We will also learn some other practical skills like how to debug, use simple tools like GDB. We do not use fancy tools. As you can see that, the biggest chunk is still operating system, but we cannot go that far because we only have 1 semester. We do have another graduate level course of operating system in the college, which is a 6,000 course for graduate students. And that one talk about operating system implementations. So it will be much more detailed, and you will need to develop different OS modules in that class. So in this class, we do not really develop that, but we're going to look at open source code, how those were developed. So we have roughly 14 weeks, I believe. This is the first week. And every week there will be an assignment, several labs. There will be 2 exams. October, the middle of October, we will have exam 1. And also I will be out of town last week. So there will be 1 exam and another class I will try to deliver online. I do not want to have substitute teachers, so I will just deliver that online. Okay. I do not promise to deliver that class exactly the time. Anyway, I will record everything. Yeah, but then I will invite you guys to join live as well. There are no finals for the class. Okay? Only 2 midterms. The midterms will be some code reading, some concepts. Then it's mainly about writing code, understanding code. So, like I said many times, we don't have an OS class, and this is called the computer systems class, right? But we are still using OS as the lens to learn difference. So why are we doing that? Why OS is still what we choose when we want to learn computer systems? There are many other different computer systems, right? So basically, it's because OS is a middleware. It's something in between. It abstracts the lower layers and provides services to higher layers. And all our computer systems, they somehow play the role of a middle layer, right? So imagine hypervisor. Hypervisor also works on top of CPU, physical layer. Then it provides services to OS. So it's a middle layer even lower than OS, right? Then thinking about the blockchain. Blockchain, you can say it's on top of internet protocols. Then on top of blockchain, you can develop different applications. You can develop a smart contract, right? So it still abstract the lower layer and provide service to the higher layer. So the middle layer, the concept of middle layer is very, very powerful. It abstracts low-level details, provides high-level interfaces, and it's crucial to understand how to design this kind of middleware. And it enables many powerful things. And operating system is one of the most important middleware computer scientists, computer engineers have ever designed. And it's still a very active field. So we have been developing OS for maybe 70 years, 80 years, but it's still a very active field. many knowledges, many philosophies you learn in this class in OS can be applied to different layers. In particular, operating system brings hardware and applications together. Applications, so my understanding is many of you have already taken a Java class. You have been writing in Java, which is a very high level language that abstracts away many different things, right? Then operating system will manage CPU's memory storage network. And when you develop Java applications, you do not have to think about all of those details. But if you write a C language, a C program, you probably need to, or C can give you the ability to think about those things, to directly control those things. That's why we are using C in this class. And also, operating system is so complicated. It's an integration of many different fields of knowledge. It ties everything together. So how many of you have been taking algorithm design course or data structure course? Okay, then there are many different data structures we were used in the OS kernel, and the scheduling itself is a very complicated problem. Even before the existence of OS, we have scheduling problems in factories, right? So those things are beyond computer science. The hardware layer, you need to learn different instruction sets, different architectures, memory hierarchies, programming level, C assembly, how to debug those, scheduling, synchronization problems. We're still working on those kind of problems right now in data centers, in microcontrollers, in many different architectures. So obviously, computers, it's a lot of magic, right? There's no magic in computers. So for people who are not computer scientists or computer engineers, they are just regular users of computers or phones. They always feel this is so magical. But for you guys, you need to understand everything about it. So there is actually nothing magical about it. It's just ones and zeros, right? So in this class, we are going to learn how to combine those ones and zeros, abstract them away. Eventually, we provide something looks magical, right? So computers rarely make mistakes. They do make mistakes, but rarely. So most of the mistakes, errors you encounter, or whoever use computer encounter, or whoever program computers encounter, those are errors introduced by us, by developers, not the computer itself. They make mistakes, but rarely. So for us to understand why we are making those mistakes, we need to understand how computer works, right? Computer is basically doing whatever we tell them to do. So those mistakes are mainly because we told them to do something wrong, but we do not necessarily understand we told them to do something wrong. We do not necessarily understand the implications of what we asked the computer to do. That's why there are mistakes, right? So to reduce or remove those mistakes, probably we will never eradicate those mistakes, but to reduce the number of those, we need to understand fully how computer works. That's what we're going to do in this class. Okay, so we're going to understand the inner working of OS. This one. Talking about abstraction, I would suggest everyone to watch this video. This one was a 2008 Turing Award lecture by Barbara Liskov. So the title is The Power of Abstraction. Okay, so this is her Turing Award receiving speech or lecture, right? So abstraction is very powerful. It enables us to manage complexity by hiding the details and exposing only essential features. It supports reasoning at the right level without the need to look at all the details. So the link is available there. So you probably heard this before, right? Some computer scientists said that any problem in computer science can be solved by another level of indirection. So here, another level of indirection is one way of abstraction. It's basically to introduce another layer of abstraction, and it can simplify complex problems by breaking them down or decoupling them into different components. And what we are going to do in this class actually reflect this philosophy. OS reflects this philosophy very well. So the goal of this course, after this one, you will have a working knowledge of C, be able to finish the homework, and also be able to not necessarily program OS, but read the open source OS kernel code. And you will be comfortable working at terminal in a Unix or Linux environment. So our homework labs, they will be all Linux based. It doesn't really require you to have a Linux machine. We will offer virtual machines, and we're still thinking about providing what kind of infrastructure to you. It will be much more clear next week. So even if you are using Windows, it should be fine. Mac obviously is Unix based, so it will be very convenient on Mac. So how many of you are running Linux directly on your laptop? Oh, several. Good. Yes. Yeah, I want to see more computer science students use native Linux on your laptop actually. So I have been using Linux for decades, maybe 10 years already, and I do not encounter any problems. Another reason is a lot of the services we're using right now, they are web-based, right? So as long as you have a browser, everything can be solved. And browser obviously is another layer of middleware. On browser, you can run different applications. JavaScript runs inside the browser, and browser talks to the OS. Also, we are going to build and use tools for debugging at a low level. We're using GDB in this class to debug programs at the instruction level. We actually do that more in my software vulnerability at security class, because when you hack a software, in most cases, you do not have the source code. You only have the binary code. They are trying to get something we call disassembly. Then from there, you debug to find out what vulnerabilities it has and how to exploit them. Then you will be comfortable with basic OS concepts, virtualization, concurrency, parallelism, those kind of concepts. Better understanding of basics and the internal of OS, and also get experience working on a relatively large code base. We're not going to look at the Linux kernel, which has maybe 20 million or 30 million lines of code right now. We're going to look at XV6, just maybe 20K line of code. Okay. And we're not going to look at each line of the code, just the important parts. So this class can also help you position yourself as a systems programmer, if that is what you want to do. A lot of application level jobs, if let's say a web developer job can be easily replaced by large language model, or even fully replaced by large language model soon. But system level programming are still harder. Actually, we just published a paper recently talking about why it's so difficult to develop secure systems for microcontrollers. We're talking about very low-end IoT devices. Those devices, they are embedded systems. They were deeply embedded before. They were not facing the internet. However, now they are all connected to the internet. So they are facing all kinds of attacks. Our data centers, laptops, servers are facing. But we find out it's very difficult to secure those systems. Not only because those CPUs do not necessarily offer the security features our data center CPUs offer, but also it's hard to find developers, software developers with multiple layers of knowledge. They need the knowledge of the application layer, they need the knowledge of the OS layer, they also need knowledge of the hardware layer, right? So it's different from a web developer, which you are more application-oriented, application facing. So at least for now, the job for a system programmer is a little bit safer than web developers, but that may change soon. Okay, so we are going to use several books in this class, and they are all free, publicly accessible. The first book is Dive into Systems. I have the link here, so if you click it. So this is the first book, Dive into Systems. So look at the contents here. It talks about the C. It talks about the first several chapters are about C programming language. Not necessarily very deep, but should be easily readable for all of you. Then a little bit about computer architecture, a little bit about assembly, x86, 32-bit, and 64-bit. That's exactly what we are doing in this class. And also ARM assembly. We don't do ARM in this class. So if you participate the embedded CTF I was talking about, then most likely you are going to work on ARM. And in our research lab, most of our projects are on ARM. Then there are storage, code optimization, OS. So this is one of the book you need to read throughout this semester. We will give you the chapter numbers so you know what to read. Then another very, very good book is Operating Systems. Operating Systems are easy 3 pieces. So this book divided operating systems into several core concepts. The first one is virtualization. How do we virtualize CPU into processes? How do we virtualize memory? So virtualization has basically processes as memory part. So this book doesn't really come with any code. So it's more in talking about concepts. It's actually very easy to read. But you are going to read the chapters of this book, and also we are going to read actual source code of x86 in this class. Then you talk about concurrency, another important concept, and the persistence. So we do not really cover security in this class, even though I actually work on security, because that would be too much for this class. Okay, so this is another book we are going to read. So each chapter is basically a PDF file, 10 pages, 15 pages. It's actually very easy to read. Then those are the 2 main books we are going to use, you are going to read. Then we are going to read source code in this class. To demonstrate those concepts, to make the discussion very concrete, I'm going to show you the source code. We are going to use the x86 32-bit source code, and it is on GitHub. It's public. So all source code are just here. So there are maybe 50, 60 files. That's it. This is a fully operating OS. Okay, so it's a very small OS. Of course, there are smaller ones, but this one provides interfaces that Linux or Unix system provide. I'm going to look at the source code of this. And this OS comes with a book as well, which is this book. It's 100 pages, and it's much more detailed than the Easy 3 Pieces book. The Easy 3 Pieces book mainly talk about the concept. This one explains the source code to some extent. So there will be chapters I give you guys to read from this book as well. There are some other books, like the C programming language book, which is a classic. It doesn't only talk about the syntax and the semantics of the C library, C language itself. It talks also about the standard C library. So if you took my software security class, then you will see even this classic book, the code presented in the book has some security vulnerabilities, and we can actually hack them. Then there's our other low-level programming language book may help you, but they're not required. If you want to learn more about computer architecture, this is also a very good book, Computer Systems, from a programmer's perspective. So this is our course website. Everything you will be able to find on this course website. And we share everything with the other sections of this class. Of course, Ferd deliver the class in a different way I deliver it, but all the assignments, labs we share. We will be using Canvas, mainly just for announcement, and all of you will be invited into Piazza, and you will submit the homework assignment through Gradescope, and we already have example code available for you on GitHub. We use GitHub Classroom to do that. So this is basically the website, two sections there. Okay, so how do I teach this class? There will be lectures, obviously. The lectures include concepts, discussion of concepts, but more about code reading, live demos. There are animations on slides. There will be labs, assignments. This is a very hands-on class. So you are going to build things. You need to get your hands dirty. This is very similar to my other class, software security and vulnerability. In that class, we do not have written exams either. This one we do have 2 midterms. That one we do not have written exams. We only have 2 CTFs. It will be a midterm CTF and a final CTF, and everything is open book, because that I believe that is the environment you should have when you hack, right? You should have everything available. You can even use large language models, but it may, so far, large language models are not that helpful when it comes to advanced hacking. Of course, there are people developing systems. We even have a project to do that. So every CTF challenge in that class, in the exams, I developed a day before the exam, so you cannot really find it anywhere. So this class is similar. You have to get your hands dirty, okay? But it's not about hacking, it's about building, right? So since you do not really have experience in programming in lower level languages, like C or assembly, so some people will argue C is a high level language, but I still think C is a low level language because C allows you to do very lower level stuff. Some other high level languages like JavaScript, Python, they do not allow you to do that. Rust is to some extent trying to replace C. It's very fast and it's secure. Because you can do very lower level stuff with C, it's not secure. Okay, the compiler, the runtime environment doesn't really confine you enough to do safe things. You are going to do a lot of unsafe things, and sometimes it's very difficult to debug a huge C program. It's difficult to understand where the bug is, right? So you may make a lot of mistakes, but we are here to help you. We have in total maybe 11 TAs across all the sections here to help you. And do not be afraid to ask questions. We will be available. Come to our office hours, or if you need any other discussion, shoot me an email. We can schedule other meetings. So when you ask questions, try to be very specific, right? Do not just say, hey, this one doesn't compile. Give us what you have done, what kind of error messages you are getting, as much detail as possible. So we were trying to help you there. So like I said, I think you already took some kind of programming class, Java or JavaScript level. But programming at a lower level, it's a little bit different because you need to know much about the CPU, how computer works. We will do 32-bit and 64-bit both. The operating system we're looking at, x86, is 32-bit. A lot of the homework you are doing will be on 64-bit. C, even though C has so many issues, it's still a very powerful language, and we want you guys to learn C because it doesn't abstract away all the things. Because it is low level. Understanding C and the programming in C, where we teach you how memory works, how CPU works, how hardware works, how you can control hardware using software. And most of the operating systems we are using now are still written in C. Of course, you can write the operating system with assembly language. You can write anything with assembly language, but it will be much more difficult. So I don't know about you guys. I still play a very old video game that I've been playing for decades. It's called a roller coaster tycoon or something. Yeah, so I think I played this roller coaster tycoon 2, maybe. Yeah, so it developed like 20 or 30 years ago by a guy who developed everything using assembly language, right? Which is there are still videos on YouTube trying to exploit all kinds of bugs, glitches of that game. I still play that. So every time I think about that, this is amazing. How can you someone write such a complicated program just in assembly language, right? So we're not going to do that. We're more using C now, and there is a trend of replacing C using Rust. However, it's not that easy. First of all, when you develop low-level programs like OS, like firmware running on embedded systems, you need to do a lot of low-level operations, like directly dereference some memory, and the peripherals are usually also mapped directly on memory, and you need to directly reference them. And the safe Rust doesn't really allow you to do that, which means you have to switch to unsafe Rust. But when you switch to that, it's similar to C. You still have those kind of bugs the C programming language has. So there has been some development in the Linux kernel to replace part of the kernel to Rust, but it's not moving that fast. Some people argue Rust may not be the language that replaces C. Maybe another safe language after Rust, maybe. Also, I think the White House last year had a white paper talking about how we should switch to this memory safe programming language like Rust, but it will take a long time because imagine the Linux kernel has 20, 30 millions of code. You cannot go. Even let's assume you can replace everything. So how do you do that in a very scalable way? Right? Of course, there have been research talking about using large language model automatically translate, but they are not working very well so far. Okay, the evaluation of the class. This class is about to get your hands dirty about reading code, designing code, writing code. So most of the evaluation is about the code you produce and the correctness of it. There will be 10 exercises, quizzes in the class. I also use that to check attendance. There will be some assignments, maybe 8 of those, and 2 bigger projects. So the labs will be smaller assignments and help you build the background you need to finish the bigger projects. There will be 2 exams, 30%. So the grade will look like this. We're not going to curve the grade. We have 3 sections. It will be a nightmare for us to curve, so we're not going to do that. 8 programming assignments, 2 bigger projects. The first 4 assignments are individual based, so you have to finish by yourself. Then the remaining assignments, you can find a partner to do that. So it's your responsibility to find a partner to finish the assignments. So there will be 2 projects. They are bigger and longer. Much more substantial programming exercises. NAPs, like I described already. They are smaller projects and they help you to build a background to finish the bigger projects. There will be some quizzes about concepts and also code reading part. It will not be that difficult. I already talked about this. You should bring a laptop to the class. Even Windows works, but if you have a Linux or Unix-like environment, that will be even better. As far as I understand, even for Windows, right now you can install something. So you have the Linux-like interface there. They provide. So basically, what I believe, I think that's WSL. So basically, Windows will expose some system calls that similar to Linux, right? So what the OS does is provide service to the higher layer. We discussed about that, right? So higher layer are applications. So how does the higher layers use the services provided by the OS? That the mechanism of that is called a system calls. So different operating systems, they provide different system calls. It's not really something standard. Okay, so Linux or Unix-like systems, they kind of have the standard POSIX. For example, Linux maybe right now have 400, 500 system calls. I believe Windows have more. And this system calls, they have a name. They have their own convention to pass parameters. So most Linux systems, Unix-like systems, they have the same system calls, the same standard. But Windows has totally different things. So if you want to run Linux applications on top of Windows, so how do you do that? So when an application makes some system calls, it's like talking a totally different language. So that's why you need another layer of translation to translate the request from the Linux applications to the language the Windows kernel can understand. Of course, there are also some other projects to translate what Windows applications asking for to what Linux kernel can understand, like the Wine projects, right? So some of you probably have been using this, especially if you want to play video games on Linux machines, you probably need to use Wine because most video games are developed for Windows systems. And you want to run them on Linux, then you need another layer there. So it will be much more convenient if you have a Linux machine or Unix machine, because then you are going to look at the native interface we are going to talk about in this class. But we are going to provide you with some other environment, so you don't need to worry about that. Requests for regrading. So you will have 3-day window to request regrade from the TAs for the homework. Okay, keep that in mind. Of course, your first assignment is to read the academic integrity policy. You guys are either third year or second year, so you should be familiar with this. But still, read this before every semester. If you have DAS, please inform me in the first 2 weeks. So to sum, how do we be successful in this class? Read assignments, assign the readings before class, ask your questions, try to answer other people's questions, get your hands dirty by coding. You do need some conceptual or theoretical background, and that's what we're going to cover in the lecture. And the projects, the assignments sometimes can be really time consuming, especially at the beginning. Okay, so start early. So our first assignments will be out tomorrow or the day after. So do not start at the last moment. Some of them actually require you spend maybe 4 or 5 hours. Okay, especially when at the beginning you are not familiar with this. Any questions regarding the logistics? We're good. So we still have 1 hour. Say. We still have 45 minutes. Okay, then let's move forward. We're going to cover a little bit background about C, compiler, computer architecture, the first week, basically this class. So this is what a C program looks like. This is a obviously a very simple C program. It's just a hello world program here. It only has like 1, 2, 3, 4, like 5 line of code, right? So on the top, this is called some directives. So this is not really a statement. So this part will not be executed by the program. This part will not be compiled into any instructions. So eventually, whatever program you write, it will be compiled into some instructions, either instructions for the CPU or the instruction for some virtual CPU, right? So if you write JavaScript, they will be compiled into instructions that a virtual machine can understand. And if you write a C code, it will be compiled into directly the CPU instruction. That's why there is a concept called cross-compiling in C, right? So you can compile a program for a different architecture. You are running the compiler. Let's say I develop a lot of ARM applications or firmware, but my laptop is an x86 laptop. So my compiler is not generating program that can be executed on the machine that the compiler executes. So that's called the cross-compiling. So some other parts will be compiled into the CPU instructions. So here we have one main function here. And for C programs, there is always a main function. That's the syntax of C. And you can consider that main function as the entry point of whatever the developer developed. So there is only one main function in a program, no matter how many C files, header files you have. But that entry point is not really the entry point of the program. It's only the entry point of what the developer developed. The C program you develop like this will be linked with many library functions. And especially the standard C library function. And the standard C library function will provide something called __ start. Usually that is the entry point for your program. Yeah. Now here, the reason we want to include this file is this is a standard input-output header. So this is a header file. So in this file, it will declare the function puts or function printf, which this program will use. So if we do not declare that, if we try to compile this, then the compiler or linker will say, this actually compiler. The compiler will say, this puts function is not defined anywhere because it's not defined in this file. In this file, we're only calling this one, right? Then we have a string here, hello computer systems. So what's interesting here is where is the string stored? Right? It has to be stored somewhere. So this part is actually stored in the read-only data section. And even if here the input looks like the string itself, but under the hood, the input to the function puts is not the string itself. It's only the address of that string. Okay. So we can look at this later by looking at the summary code. Now after that, this function returns something. Okay. So we have so this int here is a return value. So all of this is very similar to whatever language you learned before, like Java. And in those, so this pair of parentheses, you can have parameters. In this case, we do not really have parameters. And between the pair of braces, we have the body of this function. Right. So the whole thing is one function. And there are many other functions will be linked to this program as well. So if we want to compile this program, we can use GCC or Clang. So Clang is part of our LLVM project, which is an open source compiler. We use that a lot in our research because in a lot of our research, what we do is we need to, let's say, we do security, right? So if you give us a piece of C code, we're trying to make this piece of C code or the binary generated from this piece of C code secure. So how do we do that? We will instrument more code into your C code. We're going to wrap your C code with different security layers. And that step is called instrumentation. And you can do that with all kinds of compilers, including GCC. GCC is also source, but it's much more difficult to implement that in GCC. GCC has been a compiler has been there for 30, 40 years. Then LLVM is another modular compiler, which is enable us to easily implement those kind of instrumentations. That's why in our research we use CLAN or LLVM a lot. In this class, you can actually choose GCC or CLAN. So they share most of those options when you compile this any program. So for example, here, if you want to compile this program, you were in terminal, you will type CLAN or GCC, then the name of the C code, in this case, hello.c, then you want to output a binary. So that dash O there is say specify the name of your output, right? In this case, the binary we just call it hello. So hello.c is our C text code. Text, that's a code, source code. Hello is the binary. We're going to show a demo soon. So this slide shows the process of how you compile C code, and also eventually it becomes executable or file in your file system. Then eventually you can run that file. It becomes a process in your operating system. So let's say you have a hello.c here, which is a text file. It's source code. Human can easily read this. It will first go through a preprocessor. And in GCC, the preprocessor actually have a name CPP there. This is not a C++ thing. It's just the tool name is CPP, preprocessing. Then after that, it can generate a file called hello.i. I means intermediate file. This file is still a text file. So this file is not necessarily outputted or stored in the file system when you compile C program. So usually, if you just use command like this, here you are not really outputting those intermediate files. So today, later in the demo, we are going to say how we can input those files. So basically, we use some other options like save terms. It will save all those. Right? So later we're going to say the .i file. So .i file is still the source code text file, just preprocessor added something there. Now after that, it goes through the compiler. So the compiler doesn't really directly translate the C language. So the .i file is still C language. It's not directly translating C to binary instructions, the CPU instructions. It doesn't. It actually translates it into assembly languages. Okay. Then the assembly languages is still text file, goes to the assembler, which is another very mature tool. Then it will be compiled into .o file, which is called the object file, and the object file is already binary. So each .c file will become a .o file. So imagine you are programming a very large project, same as what you do with Java. You will have different Java files, right? So each of them, you can decide what you put there to make your development easier, right? To better manage your project. When you develop a big C project, the same thing. You have multiple hundreds of .c files and some of .h files. Then each .c file will eventually become a .o file, which is a binary. Okay, so that step is called the whole thing is called the compilation process. Now after that, you may still want an executable. You need to combine all those .o files together, right? So that is the job of the linker. So linker will link all of your .o files together, and maybe some library files, depending on the libraries are dynamically linked or statically linked. Okay. So after that, you will have an executable, hello there. Then this is what you can run in a terminal. So we can do that. We can do a demo on my platform. So I'm supposed to show this on my laptop, but somehow it's not. I don't have a converter here, so I'm going to use my terminal, my platform. So this is actually my platform for the software security class. I developed hundreds of challenges all over the years. So they are binary, you can hack. For example, this is for buffer overflow. This is for format string. This is for return-oriented programming. This is for heap exploitation and some others. So what about also reverse engineering? So how this is developed is like you click one of those challenges, you run this challenge, then under the hood we will create a Docker image for you. Then you just click terminal, then you can play with that. Okay. So that's why this is web-based. You don't need to install anything. As long as you have even a tablet, you can play with that. Then here there is a program. So in this case, it's format string 1, right? So this is a vulnerable program. And you can see that this program somehow have a different color. The background is pink, red here. That's because this program is a set UID program. Okay. So in Linux, a set UID program will have the privilege of the owner of the program, not the privilege of who is executing this program. So there is a file on the file system called flag, and this file is read only. So here, when you log in the system, you are logging as the user CTF, which is not a privileged user. Then as a user CTF, if you try to read this file, you will not be able to read it because you don't have the permission. However, this program is a set UID program. So when you run this program, the program will have the privilege of a root. But the program, it doesn't read that file. The program has a vulnerability, has a bug somewhere. You need to exploit that bug and use that bug to read the file. So all the challenges on this platform is developed that way. Okay, so today we're not going to do that, obviously. What we're going to do is we're going to try to compile a simple C code here. Since I don't have it here, so I need to put it somewhere. Go to temp. So I can write temp here. Okay, let's just say write hello.c file. Then I just use Max here. So we're going to type the simple program we had there, include std means standard library, IO means input output. So this is a header file in the standard C library. Then we're going to have a program, a function main, and the main function will only have something very simple. We're going to return 0 first. Before that, we're going to call the C library function puts. Hello, oops, hello, CS. Okay, so that's it. So obviously there are other C library functions you can print things like the printf. Yep.
But if you go to the purposes for like style, like the times.
Not really. Yeah, because after you compile the binary, it doesn't really matter. Yes. Yep. Okay, so let's save this one. So now we have this file hello.c here. If we want to compile it, let's see if we have clan. Oh, we do have clan here. Good. We can use clan or GCC. Then we use hello.c. So in this case, if I do not specify the output, it will always generate a file called a.out for historical reasons. So if we do this, it actually generates of executable a.out here, and we can run this one. And run a.out, and it will just, let me make this a little bit bigger. It will just print out hello CS 3650. And here you can see there is a new line. Okay, that's the difference between the function puts and function printf. If you use printf, the f here means format string. If you use, let's revise this a little bit. Instead of using puts, oh, that's because I changed it. Instead of using puts, we can use another C library function like printf. So then we compare it again, run this program again. So we can compare the difference here. So when we do puts, it actually print out this line, so there is a new line, right? So here is the new line. Those two are not at the same time. But if we do printf, it's actually not showing. Okay, it's not because it's not really outputting. It's because when you use printf, it will have an internal buffer to store what you are going to print out. And this program accesses so fast. Before this program actually printed out, the OS already killed this program. But if we add, not connected, Mac speaker. If we add a new line here, then we will be able to say the new line. Right? So with printf, we need to add the new lines in. So that's basically the difference between different functions. Okay. So in this case, you can see that we're not saving any. Why it's not showing? So in this case, we have the source code, we have the binary program. We're not saving anything intermediate here, right? So if we want to save that, go back to our slides. We need to use this command, save terms. Let's do that. So this warning means giving out all the warnings. So let's do that. Now, if we do an ls again, we can say there are several new files. Okay. Those are the intermediate files created during that compilation process. We have the source code.c. We have .i, right? It's still C code. We're going to look at that soon. Then we have .s, which is assembly code, still text. Then we have .o, which is binary. Right? BC here is some kind of a binary form as well. So let's first look at the .i file. Let's first look at the source code. Okay. So the source code, you already look at it. We have 5-6 lines, include the main function. That's it. Okay. The source code will go through the preprocessor. So the preprocessor in this step will look at the directives. So here, the directive here is to include this file, okay? Which means this file, which is a .h file, will be included in the output of this step. That's why if we do a hello.i, give us the output of the previous pre-processing step, you can see our source code is still at the end. The compiler didn't touch it. Okay. What the compiler did is adding a lot, not compiler, the preprocessor did is adding all those definitions. Okay. There are maybe hundreds or thousands lines of them. And they are in the standard C library in that stdio.h file. So this step, the pre-processing step, is only doing something like this, very simple. Now after that, we get the, after that, we are going to compile that .i file into .s, okay? And .s is still text file, but this is in assembly. This is not in C programming anymore. We still have some of those header files. Oh no, that's the previous one. Starts from here. it starts from here. Okay. So after this is our output, which is a symbol file. And the dot text means everything after this should go to the code section. Dot text means code. Then we define file name. We define there is a global variable called main. That's a function name, and the main function is actually here. This is those are the instructions. Those are eventually what the CPU executes. So this is what we call the AT&T syntax. At the beginning of the registers, there is a percentage sign. So in this class, we are going to use the AT&T syntax. Looks like this. There is a rather popular syntax, which is equivalent, but popular is the Intel syntax. So those CPUs were originally developed by Intel, but somehow the AT&T syntax get popular. The reason why the syntax I'm using in my software security class is Intel syntax because it's more natural. The syntax is similar to other architectures. But the reason we're using the AT&T syntax in this class is because the code, the OS code we're looking at, the x86, when x86 embed assembly languages, it uses the AT&T syntax. Or even you look at the Linux kernel, when they embed assembly languages, they use AT&T syntax. So here, what we have is we are going to, this is an instruction for the move. Q means what? Means we are going to move 4 bytes. 8 bytes here. 4 words. Each word is 2 bytes, 8 bytes. We're going to move from the register RSP to a register RBP in this case. So percentage sign here means after that, this is a register. There are so many different registers, which we will learn the first class next. Then there are other instructions. So the whole thing, at a C code level, we have 3, 4, actually we only have 2 lines in the main function, right? Print, we have return, just 2 lines. But after we compile this into a real program, there are maybe 10 instructions like that. Right? And there is a call to the library function printf here, which is that printf we had in our C code. So here is a call. And before the call, we are preparing the parameters for that function call. And then we're going to clean up the stack and everything. So that is what the assembly looks like. So the assembly eventually needs to be assembled into binary code. That's why we have that hello.o file. Okay. So if you use file to this, then you can say file is a command to tell you the type of a file based on some signatures, based on some magic values. It tells you that this is a binary file, and there are symbols. That's not a strict means there. There are symbols here. If you do a file on hello.c, it will just tell you this is a ASCII text file, even though it's a C source code, right? Or if you do I, you get a same results. This is still a C source code, but an ASCII text file. So then, since we do not have other .o files, this .o files will be linked with the library and become the eventual executable, which is hello. So if we do a hello on this, file on this, you can say this is a program compiled for x86 34-bit. It is dynamically linked, which means the printf function, the C library, is not really in the executable itself. Okay. So when this program is loaded into memory, becoming a process, when it calls printf, printf will already be there. Maybe other programs already loaded in the memory space. And the different programs are going to share that library. So we don't need multiple copies, duplicate those libraries in the memory. So this is a technique we can use to save our memory. This is dynamically linked. So this is how we can compile C program, and you also get the intermediate files. So another tool we use a lot in the software security course is this obj dump. So the input of this command is just the binary file. Then use the -t, we're going to disassemble this binary file. So in this case, our input is not the source code. We don't have the source code. We only have the binary code. We want to understand what this binary does. So if we try this. So D here means disassemble. Then we can disassemble this program hello. Then you can get all the text section or code section of this binary. As you can see, there is a elite function, underscore elite function. We didn't program this function, right? We only programmed one main function. But this function is there because the C standard library has it. Then there are some tables, PRT table. This is actually important for hacking, but not important for this class. Then there is a printf function. This is actually only a stub of that function, not really the function, because like I just said, this function is not really in the executable. This function is in the C library, and many different executables or processes, they may share that standard library. So in this executable itself, it only has a start for the function. Then we have the underscore start function, which is the entry point for this executable, for this whole program. That's the entry point. We didn't program this, right? So everything starting with underscore, we didn't program that. That's part of the C library. There are some dynamic link allocator functions, deregister functions. We didn't program this either. So those are also from C library. So what we did program is the main function. Okay, look at this. This is very similar to what we look at for that assembly code, that .s file, right? It's actually they're supposed to be the same thing. The .s file are already instructions. However, they are readable text. They are not really instructions. They are still asking. Eventually, they compiled into binaries using the encoding of the CPU instructions that the CPU understands. Okay, so what we are saying here is directly regenerated from the binary. So what happened here is at this memory location, there is a hex value 55. This is a hex value, and that hex value 55 to CPU means that's the instruction push RBP. We are going to push the value of that register onto the stack. Okay. So that is the first instruction we had in the assembly language function. Then we have this one we talked about. We move RSP to RBP. This is another instruction. And this instruction has 3 bytes. That's 48, 89, E5. That's the CPU encoding of that instruction. Okay. So here what we are reading is what this tool generated for us. In this program, we only have this, right? For example, that would be, let's just do this. Okay. Then we have another function called, that's what I have there, to function printf, right? The several other functions. So I have several other instructions. And they're not very big. This is 1 byte, 3 bytes, 4 bytes. This one is a little bit longer. Here, this part is part of this actually. Yeah, so this is the 64-bit version of this program. And of course, we can compile this into a 32-bit version. Let's try that. 32 bits. I guess we can do M32. I think that's the command. Yeah, it works. Okay. So now we compile this program again. Now we generate another binary program. We put a file on this. You can say previously it was x86-64, right? So now it becomes 8386. So this is a 32-bit program, not a 64-bit program. So both 34-bit program and the 62-bit program works on a 64-bit machine, obviously. So if we disassemble this one again, you can see the functions, the instructions will look different. This is the main function. They're from the same C code, but the instructions are different. Previously, the first instruction was push RBP. Okay, the register name is RBP. So now the register name becomes EBP. EBP is a 32-bit version of the base register. The RBP is a 64-bit version of that. Then we move, and somehow I think the program may be a little bit longer than before, almost the same size. So most of the instructions are similar. This is a simple program, so most of them are similar. We're still calling the printf function in this case. So in your homework, you were programmed in 64-bit, which actually is easier. It's a little bit surprising, but programming in 64-bit is easier than 32-bit. The reason is 32-bit, you have all kinds of restrictions, and you need to take those restrictions into account. That's why programming is harder, but 64-bit. So that's what we have for this. So next, let's talk a little bit about computer architecture, the hardware side. So CPU is obviously the brain of the computer, that's a hardware. So one CPU core can only execute one instruction at one particular time. Okay, so this is not very accurate anymore. There has been a lot of advancement in computer architecture. If you look at your CPU, you may say there are different hardware threads, right? Let's see if we can do that. Because here we have virtual machines. Let's try to do a CPU. So LS CPU give us the information of the CPU we are using here. Let's say how many cores we have. So here it says it has 8 cores, and each CPU core has one thread here. Okay, but some of the newer CPUs, one core have multiple threads. They are not the OS level concept of a thread, but the physical threads. In those CPUs, technically one core can execute multiple instructions at the same time. Basically, each thread, physical thread, they will share some resources, but they have their own resources, like they have their own registers, but they may share some execution units. But for now, for us to easily understand this class, let's say one CPU, one core can only execute one instruction at one time. And one CPU may have multiple cores. Even our phones, they may have multiple cores. Then we measure the speed of the CPU executes at the megahertz or gigahertz level, right? So megahertz means 10 to the power of 6, gigahertz means 10 to the power of 9. So one of our projects right now we're doing is we're trying to do microsecond level context switch in virtual machines on some new CPUs, which means we are trying to execute just thousands of instructions before we switch to another application. So that's what we're trying to do. Right now, Linux, usually their context switch takes 3 to 10 milliseconds. We want to reduce that to hundreds of microseconds. So CPU obviously has registers, has some computing modules. The PC here is not personal computer, it's a program counter. So every CPU has a program counter, every core has a program counter. It indicates the address of the next instruction we are going to execute. Then the CPU is connected to other modules on a computer. For example, the next most important thing in a computer is the main memory, right? Usually it's a dynamic RAM, DRAM. CPU is actually SRAM, which is very fast. DRAM is a little bit slower, and DRAM is usually not part of the CPU die. So this is one die. So everything else is on a motherboard. But now we have seen recently we see a lot of things be integrated into the CPU. For example, we have this bridge, this I/O bridge. This bridge connects the CPU with the main memory, and because memory is very important, we wanted the memory access to be very fast. Of course, it's still hundreds times slower than directly accessing something inside the CPU. The bridge we have here, we used to call it as a North bridge. Okay, so now the North bridge, you do not see this chip anymore. We see more and more CPUs just integrate the North bridge into the CPU, and we have other more some other slower peripherals like the USB, like old graphic adapters. But now the GPU they will go here because we need them to be very fast. Or disk controllers. So those will be connected to another I/O bridge. 20 years ago we called them the South bridge, but the South bridge is also integrated into the CPU now. So if we look at this is a picture of a very old motherboard. So this is a socket for the CPU. There are different packaging methods so I remember my old Pentium 1 CPU maybe. It's kind of like a house, like this big. And it doesn't have like this kind of a flat socket. Then those are for grants, and this is probably the North bridge. So this is a North bridge chip, but you don't really see this a lot anymore. They have been integrated into the CPU itself. The South bridge has also, so this one is called the South bridge. They are for slower I/O interactions, and they have been integrated into the CPU as well. So those are for even slower things like the hard disk. So this is another image of older ones. This is for hard disk, different types of hard disk. This is for RAM, CPU, North bridge, South bridge, USB. So USB, this USB hard disk, they eventually connect to South bridge, and South bridge eventually connected to CPU. And the RAM or maybe GPU or maybe some faster PCI will connect to North bridge, and North bridge will connect to CPU. And North bridge obviously is faster, more expensive than the South bridge. So OS. You have been using all kinds of OS, and the word OS is somehow overloaded. You have been talking about the Linux. We're talking about Ubuntu. I run Ubuntu on my laptop. So Ubuntu is actually more like a distribution of Linux. Most of the Linux distributions, they have the same Linux kernel. So when we talk about operating system, it actually means several different things. The first one is the OS kernel, right? That runs in a special privilege mode of the CPU. Then we have other tools coming with that OS, but they are not really running in the kernel mode. So Windows come with all kinds of tools, Mac come with all kinds of applications tools as well, or even Linux. But there are two main classes of CPUs. There are two main families of OS. The first one is POSIX based. So basically they follow the standard of POSIX, including they started from Unix. There are not so many Unix systems anymore. Most of what we are using is Linux based, but Linux also follow POSIX standard. Mac is built on top of BSD actually. Android is just another layer on top of Linux. Android is actually a Java runtime layer on top of Linux, customized Linux. iOS, I believe, is also based on BSD. And so they share the same interface. Then another family is Windows. These are developed by Microsoft, and they have a totally different interface. What we discussed before with WSL, Microsoft or Windows is also trying to provide POSIX interface there for applications. There are many other customized OS, especially for what our lab work on. We work on a lot of real-time OS, RTOS, and those OS are specifically designed for low-end IoT devices. And right now, and most of those devices do not have memory virtualization, which is a big topic of this class. So those systems right now, we do not have many standards there, and we have several different OS getting popular in that domain. So Linux is developed many years ago by Niners, and in 1991 started as a hobby, and this was the initial email he sent out to a mailing list. I believe it's a Minix mailing list. So Minix here is another operating system developed by a US professor who lives in Europe. So this operating system has very good design. It's a micro kernel architecture. However, the professor never open sourced that. Actually, now it is open source, but before Linux, he didn't open source that. The Niners saw the opportunity, developed his own operating system for fun, for hobby, then open sourced it. Then it took off, right? So 30 years ago, he was like, I was doing this for fun, won't be a big or professional thing, and it's probably not portable. It's not going to work for many different architectures. But now Linux works on every architecture. It's a huge ecosystem, and every one of you can also contribute to this project. It's an active project. And in our lab, we also work on some kernel projects to secure the kernel and secure the applications as well. One part of this class is you need to get familiar with some command line tools. I already showed you the terminal, and that's what you are going to use in this class. There are many different command lines, and with the large language models, you can easily find the command you want to use. We showed you how to use actually ls today. That shows you what the files in the directory. There are commands like cd, pwd. Cd is change directory. So cd is not really a program. So when you type ls in that terminal is called a shell. So what that shell does is it will create a new process, and that new process runs the program ls. So ls is actually another program stored in the file system. But if you type cd there, it's not running a new program. It's just a built-in command. Okay. pwd, the same thing. If you want to look at what the CPU is doing, then you can do something like htop. We don't have htop here. We have top here. Yeah, we do have top here on htop. So it tells us, where is it? Here. It tells us we are running 4 programs. 3 is sleeping, 1 is running, and what are those programs? How many CPU, how many memory they are using? Okay, htop is a much more user-friendly tool to do the same thing. Those are the commands you will learn later. Also, you can write a shell script. Yes, we can sweep this until we get there. Also, if you don't know what to use, what command to use. Now you can refer to large language model. Also, there used to be the man page for things. If you want to know how to use, let's say we just use top, right? So what does top do? We can man top. So it tells us top is a command and what it does. And here it's interesting, it said top what? That means that's the section 1 of this man. Then if we do a man printf, we have been using the function printf. Man printf. Then you can say this is a function. Oh, this is a command as well, to the function level. One, two. Okay, it's almost time. Let me see. Let me wrap up really quick here. The other things are not really important. We're going to use x86. So from next Tuesday, we are going to learn the 32-bit and the 64-bit CPU first. And then we talk about how to program in assembly for that CPU. So the whole next week, we will be doing that. The week after, we're going to talk about the C programming language for a whole week. Then we are ready to jump into the OS. Cool. See you guys next week. Thank you.
You guys have like.
Yeah.